Sorry, is it just me or is the audio not working?
Here. All right. So now I'm not muted anymore. Can you hear me?
Yeah, thank you.
All right. Great. Okay, so basically I just said I'm happy to be here, and now comes the talk. So some kind of motivation here. Oh. Yeah, I think okay. Motivation. Aha, okay, so here comes the motivation. Okay, so problem or not, I mean, maybe it's not a problem, but I mean, the axiomatic description of non-commutative Riemann spin geometry or manifolds does not incorporate principal bundles. So let me just say what I mean by this. Usually what people do, I mean, nowadays people are interested in the geometry of non-commutative spaces, so topological properties have been pretty well understood. So people went over to study one way to do it, spectral triples. So where this usually is some, dense star algebra of a C-star algebra. This is some Hilbert space when you have a phase-ball representation of A on H, and this is your direct operator. To connect this to what we have seen before, I mean, you take the functions on a manifold. I think Stefan used an M maybe. So what is the H? I mean, basically what you do here is you take the sections of the spinor bundle and then you complete it with respect to some inner norm that gives you the L2 spinors. Yeah, I mean, this will be the H, and then this is the direct operator. All right. Maybe another thing is that Kohn proved in the 2008 something, like if you have a commutative spectral triple, so A is commutative, and then you have a couple of conditions, then this always comes from a manifold. So I mean, saying the spectral triples as somehow a non-commutative version of spin manifolds. Anyhow, well, it's not so easy to come up right with the direct operator. I mean, you start with any C-star algebra. How do you study its geometry? And so this is basically what I would like to do in this talk, to show you, like, you start with the C-star algebra and then you use principal bundles to come up with spectral triples. Okay, so I mean, this is basically what I was saying. So I would like to use the framework of non-commutative principal bundles to study geometry of non-commutative spaces. And I mean, this is part of a bigger research project, and I mean, like more or less 4 steps. I mean, first of all, so what you would like to do is if you have a geometry on the base space, you would lift it to the total space, right? In a C-star algebraic setting, you don't have geometry, but if you have a geometry on the base space, you would like to lift the geometry to the total space. So I mean, this has been done. Then you would like to say something about the frame bundles. You know, this is also something we saw in the talk. You have these frames. So you would like to say what is a non-commutative frame bundle as well. So I will briefly mention this. Then basically this talk is about the part 3, how you extend principal bundles by group extensions. And once you do this, once you have done this, you have all the ingredients, you can try to find interesting spin geometries. All right. So some conventions, you will see P and X's, and these will usually be compact spaces. So I'm in the compact category, yeah? Everything will be either compact or unital. A's and B's will be unital C-star algebras. G will be a compact group. Well, some of the results can be generalized to compact quantum groups. Representations will always be finite dimensional and unitary. Then, I mean, this is a representations are denoted by sigma usually. And this ER of G will denote the set of equivalence classes of irreducible representations. And some of the results are much easier to state when the group is compact abelian. So whenever I have a group, then I write G star for the dual group. All right, so just to give you a small introductory. Okay, and then let's talk a little bit about non-commutative principal bundles. So first of all, I would like to tell you what C-star dynamical system is. And by what I mean by a C-star system is simply a triple AG alpha, where alpha is a strongly continuous homomorphism. So you have a map from G into the automorphism group, and this strongly continuous simply means that for all x in your algebra, this map from G into A, which maps G to alpha G of x, is continuous. With respect to the topology here and the norm topology here. I mean, it's strongly continuous. So we'll see in a while why I'm interested in this kind of actions. Well, wait, first of all, whenever you see a B, this will usually be the fixed point algebra of the action. So these are simply all the elements that are fixed under alpha. All right. And why I'm interested into compact groups or compact quantum groups is, right, like every continuous, possibly infinite dimensional representation, you can decompose your algebra into isotypic components. I mean, here you have the formula. I mean, there's some kind of subspaces. In fact, there are also bimodules over the fixed point algebras. And Peter Weil says that the algebraic direct sum is a dense star subalgebra. So basically, a lot of the things I'm doing is then I'm studying the subspaces and transfer the information into the whole space by this decomposition. So this is one of the reasons I'm working with compact groups or compact quantum groups. All right. Please, if you have questions, just go ahead. Okay, something easy, right? So you have the classical one torus or a circle, and then you have a map of the circle on the functions of the circle just by left or right translation, right? I mean, anyways, it's commutative. And you can show that this map here is a C-star dynamical system. All right. Okay, it's no wonder. I mean, maybe it's, well, fixed point algebra, it's trivial, so we would call the action is ergodic, so only have the constant functions. It's a fixed point algebra. And well, we also know that the irreducible representation are parameterized by the integers. And yeah, well, the isotypic components are complex multiples of these Fourier mode functions. Yeah, so the function which maps theta to theta to the power of k. All right. Then the algebraic direct sum is simply the Laurent polynomials, if you want. And then basically what you say that each function can be approximated by its Fourier modes. I mean, that's some version of classical Fourier decomposition. Yeah. More general, whenever you have a continuous action of a compact group on a compact space, then you can induce a map on the functions on the space simply by, well, you're composing the function with the action and the argument, and this will give you a C-star dynamical system, and the fixed point algebra will be, I mean, functions which are fictional, the actions will be quite actually isomorphic to the functions on the quotient space. And here everything is nice because my group is compact, so the quotient is also nice. Yeah? So particularly these actions are automatically proper. All right. More examples. Quantum tori, always a good example. You know that universal C-star algebra generated by unitary C and V, satisfying this commutation relation. And here you also have an action. You have an action by the two torus. Well, how is the action defined? Well, on a generator U, a pair of complex numbers just acts by multiplying with the first component. And on V, the action is by multiplying with the second component. And this gives you a C-star dynamical system. Okay, very nice. You might ask, what is this fixed point algebra? Well, think a little bit about this. This is, again, ergodic. Fixed points are only the constants, or simply C. And okay, again, the irreducibles, they're parameterized by C2. And the isotypic components are simply multiples of these products here. Okay, very good. Well, it's always good to have a lot of examples. I have more examples. The Heisenberg group C-star algebra. Well, okay, so what is this? I mean, you know the Heisenberg, discrete Heisenberg group. It's the upper, the the group consisting of upper triangular matrices with integer coefficients. And as the group C-star algebra is generated by three unitaries, U, V, and W, subject to these relations here. All right. So it's a nice presentation. Again, you have an action on the classical two torus. So again, a pair acts on U by multiplying with the first component. The pair acts on V by multiplying with the second component. And then you see from the relation, W must be fixed. That means the fixed point algebra contains the functions on the circle. Okay, so this is actually everything. And you get a C-star dynamical system over continuous functions on the torus. Why is this interesting? Well, this is a C-star algebraic bundle over the torus. You see, the fixed points here are the continuous functions on the torus, which makes it a CT algebra. So you can realize it as a bundle. The base space is the torus. Now the question is, what is the fiber over a given element in the circle? And here you see you get for each element, you get the quantum torus. Right, so this is a quite interesting bundle. And let me also say that, there has been a paper by Richard Nest and by Siegfried Echterhoff about non-commutative principal torus bundle. And then, they had some definition and they were classifying these spaces. And then this Heisenberg group C-star algebra appeared as a classifying space here. So this is quite interesting. All right. And then maybe a quantum SU2, which you know, right? Again, universal C-star algebra generated by two elements A and C, subject to these relations. Seen this before. And here you have an action of the classical torus. You just multiply with theta on each generator. This gives you, again, a C-star dynamical system. This is the so-called quantum Hopf vibration. Right, so in the classical case, when Q is equal to 1, you get the classical Hopf vibration, which is a bundle over the two-sphere. Structure group is a circle. And here the fixed point algebra is the so-called quantum two-sphere. Okay. So there are plenty of examples. Maybe an abstract way to construct, so I will use this a little bit later, is when you start with the C-star dynamical system and you have a closed normal subgroup, right? Then you can induce C-star dynamical system. How you do this? Well, you just take the fixed point algebra with respect to the normal subgroup, and there you get an action of the quotient group. Okay, this is all you do. Not super complicated, but this is a way to, if you have one, you can get new ones. All right. Okay, great. So now I talked about C-star dynamical systems. Now I would like to tell you a little bit about freeness. So what is a free C-star dynamical system? And we start out with the definition here. C-star dynamical system is called free if the so-called L would map. What does it do? So it's defined under algebraic tensor product of the C-star algebras. So A with itself. And it goes into the functions on G with values in A. And what does it do? Well, it takes a simple tensor xy, and then if you evaluate this and a group element, this will be simply x times alpha g of y. Okay, this is the map. And the condition as freeness means that this has dense range with respect to canonical C-star. All right. And those of you who know or have a sharp eye also see that this is a topological version of the Hopf-Galois condition. Hopf-Galois condition means it's canonical map with bijection. Actually, also what you use here is that freeness actually corresponds to the surjectivity of this map here. Okay, and then there are various equivalent notions of freeness, and at least in the compact case, they're all equivalent. So you have this notion by Riefel in the 90s called saturated actions, which basically means that the cross product is a Morita equivalent to the fixed point algebra. So this is always a nice property of freeness. Cross product is Morita equivalent to the fixed point algebra. Then you have this unitary tensor functor, so more strongly monodial actions. for those who like category theory. And then there's a notion, Peter-Weil-Galois condition, which is an analytic notion of the Hopf-Galois condition. Okay, and they're all equivalent. All right. Quick intermezzo. I was talking about principal bundles. Now I would give you like a topological version of what this is. So it's a quintuple. You have P, which is the total space. You have the base space. You have the structure group X. Then you have an action, it's called R. This is a continuous action, which is free, meaning that all the stabilizer groups are trivial. This is the classical notion of freeness. And Q is a continuous and open surjection of the total space on the base space. And then you have satisfying these two relations. I mean, the action is basically on the fibers. This is the first condition. And then all fibers are G equivalent homeomorphic to G. All right. So most of you, I mean, the way it's used in differential geometry, mathematical physics, is that you want to have local triviality. You want that the bundle looks locally like a product of open subset of X and a group. But I mean, you don't need this. I mean, this is a purely topological version of it. Yeah? Here you can have bundles which are not locally trivial. Because you will see in a non-commutative world, it's not clear what local triviality is. All right. Please. Yeah.
If the C-star is commutative, I guess this should be the same as.
Excellent question. This will be my next slide. Yeah, excellent question. Let me say like one more. I mean, here I have a quintuple with this, all this kind of information. In fact, you can always show that if you start with the principal bundle, then it factors through the canonical quotient map. I mean, you always have the map from P into the quotient space. And this induces a homeomorphism between X and the quotient space. So I mean, the quotient space, X is somehow determined or homeomorphic to the quotient always. And actually, so this quintuple can be identified simply with this free action, which is continuous. So this is all you actually need to have. All right? Okay. So here, thank you very much for the question. So this is exactly what I'm saying here. So you have a continuous action and the following statements are equivalent. Well, the action is free in the classical sense, so all stabilizer groups are trivial. All right. And then we learned that whenever you have a continuous action, it induces a C-star dynamical system. And this C-star dynamical system is free in the way it was defined by Elwood. So these notions are equivalent in the commutative case. Again, the fixed point algebra is the functions on the quotient space. And well, this justifies to call this free C-star dynamical systems non-commutative principal bundles, if you want. So this is a good framework for this kind of theory. And this is something I will use now. All right, usually if you have a framework or you have a definition, it's always good to have examples. So I learned from my supervisor, if you don't have like 5 different example classes, you can just leave it and do something else. All right? That, that ended quickly, a lot of projects. But okay, at least here I have some, okay, first maybe some motivation and then some examples. Mathematical motivation is, I mean, studying actions is super interesting. I go completely crazy, nuts if I can study actions. Usually funding agencies are not happy only with this motivation. Anyways, so free C-star dynamical systems are closely related to saturated Feld bundles. I mean, we talked about this, are to Feld bundles. This is some kind of continuous way of grading. Hopf-Galois extensions, as I mentioned, and of course, maybe those who really like algebra, strongly graded rings. So there are many connections, and you can translate. I mean, if maybe some problem is too difficult, you can maybe first study the algebraic, fully algebraic setting. All right. And then, I mean, here maybe a little bit more interesting. I mean, you have many applications in recent years, including non-commutative Riemannian geometry. Then these things also appear in unbounded KK theory. I mean, you usually try to represent these KK classes by spectral triples, and then usually are principal bundles involved. Non-commutative gauge theory. Let me just remind you that gauge theory, right, is, I mean, physicists call gauge theory is more or less equivalent to principal bundle theory. So if you want to have a non-commutative gauge theory, people have addressed this in terms of principal bundles. Brahm, for example, in 2 papers recently. And then, yeah, T-duality, which is a symmetry, supersymmetry, string duality, and quantum field theory. So it's the canonical words to drop. All right, we talked about this. Again, examples. Examples are important. Here you have many examples, I hope. So whenever you have the quantum n-torus, you have a canonical actions by the classical n-torus, and this will always be free, and this will be ergodic because the fixed points are simply C. Then whenever you have a cross product by a discrete abelian group, hey, it comes equipped with a dual action of the dual group, which is compact abelian then, and this will be free action, and the fixed points will simply be A. Okay, you have a cross product, and actually if you have twisted cross products or something which people also called cleft, basically, I mean, cleft C-dynamical systems are always twisted cross products somehow. The Heisenberg group, or the group C-star algebra of the 3-dimensional Heisenberg group, this was a free action. We saw this example. Also, quantum SU2, the action is free. All right. For a graph, nowadays a lot of people working with this graph C-star algebras, live at path algebras. And see, whenever you have a graph with finitely many vertices, then you have a canonical action. Then the graph C-star algebra is free, or it's a canonical action of the graph C-star algebra is free if and only if the graph is row finite, has no sinks. Row finite means you have only finitely many outgoing edges. Okay, so this is a characterization. And then you have the Conlandi spheres, which is basically a deformation of the classical 7 sphere with the 2 torus that admits an action by SU2, classical SU2. And this is a free action and gives you a fixed point algebra over the deformed 4 sphere. Now I'm saying here also, I mean, here the examples are usually tori, but I mean, they're also actions by compact groups. All right, frame bundle. We talked about frames. So this will give you a class of SON bundles. So you start with a compact connected oriented manifold. And when you ever have this, then you have a tangent bundle, right? And then this T small x, big X, this is simply the tangent space at the point X, all right? And then you look at this space of orientation preserving isometries from Rn into the tangent space. Let me maybe should say that the manifold has dimension n, so this is where the n comes in. Okay, great. And then the frame bundle simply defined as a disjoint union of these spaces. For each x you have one. And then you see, well, by definition, you have a right action by SON on this space. And yeah, well, actually, this is a free action. And I mean, this is only a set, but then you use the charts from the tangent bundle to give it a manifold structure. So you really get a principal bundle, which is locally trivial, and all the operations are continuous or smooth, actually. All right. Why is this interesting? I mean, I mentioned this before. So you start out with a tangent bundle. Then you can construct canonically this frame bundle, and then you can associate with the standard representation. What do I mean? I mean, you take the frame bundle, you take the product with Rn. This guy comes equipped, so this has a left action by SON. This is a write action by SON, by the standard representation. So you mod out the standard representation. And then you recover your original tangent bundle. No? So this is actually quite nice. And I mean, this is also used in this definition of spin structure, right? I mean, you start out, and this is something Stefan was explaining before. You start out with X, then you get your tangent bundle. In the tangent bundle, you get the frame bundle. This is an SON bundle. And then the spin structure is simply a twofold covering, right? So, I mean, this is the way, I mean, X tangent bundle, and then you need this principal bundle. And this is how it looks like, how you construct it. All right. Okay, so I talked about this non-commutative frame bundles before. So the motivation is, well, find an algebraic analog of this geometric inducing procedure, right? I mean, if you have this tangent bundle, there's this natural way of associating this principal bundle. And of course, I mean, here you use bundle charts and so on. So this is not so clear how you transfer this to the non-commutative setting. Now, we discussed also in the last 2 days, in general, the big question is, and I think maybe you almost solved it. I mean, so you have a bimodule M, and you would like to know if this bimodule is associated to some non-commutative principal bundle. So question is every bimodule associated to a non-commutative principal bundle? Well, here in the classical case, we know it is true, because here we can always do the trick with the frame bundle. But it's not clear if every module or bimodule is induced from a principal bundle. Something you would like to think about. All right, anyways, well, in the paper, I did some description of what kind of properties a module must have so that you can construct a SON bundle. In general, I mean, it's a nice theoretical thing. In general, if you give me a module, it's a little bit hard to see if it has this structure or not. But I mean, it's a partial result in this question about frame bundles. So again, I mean, I could construct this 3C-dimensional system with the property, if I associate it with the standard representation, it recovers my original module. All right. And also, well, the construction recovers the classical setting. So if you want, this is a non-commutative frame bundle. Okay. Also, this is an example of these free C-dynamical systems where your structure group is now SON. All right. Okay, so now you know a lot about the problem and non-commutative principal bundles. So now I would like to tell you a little bit about factor systems. This is something I used heavily and which I also used to extend this principal bundles by group extension. Again, I mean, the question here is, right, I mean, you always, if your manifold is nice enough, you always get up here, always, but here's an obstruction, right? I mean, it's this Stiefel-Whitney class. Now we can ask the same in a non-commutative world. Okay, let's say you start with some C-star algebra here. Let's say you find a module that is nice enough and has these properties, then you get this SON principal bundle. And then the question is, can I extend this principal bundle, SON principal bundle, with respect to the central extension of SON and the spin group? So this is the motivating example. And one way how I would like to address this is by these tools which are called factor systems. Okay, so you might have heard about this name from group theory. So what is the problem here? It was, I mean, Schreier and Eilenberg-McLean, they developed this classification theory of non-abelian extensions. and this leads to low-dimension non-abelian group cohomology. So what is the question here? Is so let's say you have this non-abelian extension. You have two building blocks. You have the G and you have the N. N is a normal subgroup. And okay, so if you have this, usually what you do, you choose a normalized section. Simply means that the group element in G is mapped to the group element of E. So this is normalized. And then you associate data to this. You start with the section. And what you do then is for each element in your group G, you get an automorphism of the building block N. How? Well, you just conjugate by S of G. And then you see, well, this guy must be an N, simply by projecting it down. You see, if you project this down, this lies in the kernel, and then with G to the power minus 1, so this will be 1. So this guy must be an N. So this defines an automorphism of N. All right. Okay, so for each G, you get an automorphism. And for each pair of elements, you get an element in N. How do you do this? You just see, like, you just try to understand how much S is apart from being a group homomorphism. And if it's a group homomorphism, this would be, of course, trivial. But if not, it gives you an element in N. Okay, great. So this is what you can always do. And this family of automorphisms and these elements, this is what they call the factor system. Okay. And then they could show that, I mean, first of all, well, right, the factor system now only depends on data on the building blocks. I mean, only on G and N. So you can forget about the section and forget about the E. And then you do some computations because why not? And then you have this twisted cocycle conditions. So the S's and the W's, they justify these relations. And this is the coaction condition, and this is the cocycle condition. Right? And then you can actually show that all the information about the extension is encoded in the factor system. So you only need the factor system. If you know the factor system, you know everything about E. And on the other hand, if you have an abstract factor system, remember, you only need the building blocks, N and G. You have this set, I mean, you have this factor system abstractly. You know, it satisfies this relation. You always get an extension from this. Okay. Good. So at some point I was, you know, my undergraduates, I studied a lot of Lie groups and Lie group extensions and so on. And then I was interested in principal bundles, and I was like, okay, maybe principal bundle is a little bit the same as a group extension. How so? I mean, like the total space A, the big thing, can be considered as something which can be built together from the base space B or the fixed point algebras and the group. Can I make sense of this somehow? Can I associate data with the building block B and G that contains all information about the free C-stat system? Okay. Why? First of all, I was interested in classifying this free C-stat systems, right? I mean, classically, you have check homology, for example, to classify principal bundles, but there you have this open coverings, which you don't have in a non-commutative setting. Yeah, so I was interested, like saying, like, okay, how many are there if I fix B and G? Then permanence properties. So which properties of B and G pass over to A? If you remember briefly in the beginning, I had this research program, and then I said basically, well, so I mean, these are all topological structures, right? So now if I have some geometry here, and I have a Lie group here, can I turn this into a geometric object? And the answer is yes, you can. And here I use these vector systems to lift a spectral triple and the spectral, as it I have a spectral triple here, I have a spectral triple here, and then I can use vector system theory, which I will tell you a little bit about in a while, to construct a spectral triple on the big space. Then you have K-theoretic considerations, invariants, and characteristic classes. And in general, you can use this vector system to do computations. In general, if you want to compute stuff, then, I mean, just like in a group case, you can have this vector system and try to do your best to figure something out. I mean, sometimes it works, sometimes it does not. Okay. But how so? I mean, you have this definition of freeness, Elwood condition and Hopf-Galois condition. So this is also always something that bothered me, is that, well, in the definition of freeness or Hopf-Galois, the co-invariants never played a role, if you would say this. At least here, I mean, it's only subjectivity, and it only includes the A. So, I mean, if I don't know anything about the fixed point algebra, how should I classify, right? Somehow, we needed a definition which incorporates, which can be used to find a classification. And then we managed to do this. Okay, what does it say here? C-star dynamical system is free when, for each irreducible representation, you can find a finite dimensional Hilbert space and an isometry that lies here in A times this operators on the representation space in this Hilbert space. So it's this enlarged A, amplified A, satisfying this relation here. Okay, I'll say, okay, you say, how is that useful? Okay, I will tell you in a little while. How so? Just to give you a little bit of ideas how these S's look like. I mean, there are isometries, and remember for the quantum tori, we can simply use these products here. So there will be not only isometries, there will be actually unitaries, and this is a special class of free C-star dynamical systems. When you have unitaries, you call them cleft. Anyways, I mean, this is how your unitaries or isometries would look like in the quantum torus. So you can compute them. I mean, they're not only abstract. For quantum SU2, what can you do here? You just take, right? I mean, the irreducibles are parameterized by the integers, and here for one, you take simply the column vector A and C. Okay, and this is element in this amplification, and it does the trick. Okay, and then for n bigger than 1, you just take the n-fold tensor product and multiply them together, and that's the trick. I mean, don't bother. I mean, it's just, it's simply here because, this is generated by a free group, so you can do this trick here. And then you take partial adjoints for the negative integers. Okay, so for quantum SU2, there exist homogeneous spaces. You guys like those? When you have a closed subgroup, and then the canonical right action on H on G always gives you a principal bundle over the quotient space. And this action is always free, right? But I mean, how do you establish freeness in terms of this theorem? Well, you use this Frobenius reciprocity theorem to get for each irreducible representation, like this induced representation and isometry from the representation space into this bigger space. And then you just really define this isometry as this thing here, and it does the trick. And this, this establishes freeness in an algebraic way, in terms of this theorem lemma we had. Okay, so again, so this is the characterization. How can I do anything useful out of this? So we fix now one free C-star chemical system, and by the theorem, I can also fix for each irreducible representation of finite dimensional Hilbert space in an isometry, as in the lemma. Can do this. And then by taking direct sums with respect to irreducible representation, we can extend these isometries to arbitrary finite dimensional representations. Sure, you can do this. And then for each representation, you get a star homomorphism, gamma, which you get by simply by conjugating with the isometry. And this looks a little bit like in the case of group extensions, right? There you had this automorphism by conjugating, and here you get by conjugating with this group homomorphism and this amplification. Okay. And again, you get something like a 2-co cycle simply by measuring like how far this is away from being a, I don't know, this being a group homomorphism if you want. You see that the ranges here, they always end up in B suddenly. Here's where the B pops up. Huh? This is what I wanted. I wanted something that depends on the B and the G. All right. And I also, I have this co-cycle conditions that I can use to do computations. This triple is called a factor system. All right. This is associated with these isometries. And now you might know, okay, maybe they're a bit complicated. But I mean, as soon as you're in the compact abelian case, then these crazy things are co-cycles on the dual group. So they are quite manageable, actually. And you can computations using computer algebra frameworks. All right. And here's this reconstruction theorem. What you can show is that the multiplication, involution, and the action are completely determined by the factor system. So I mean, this is exactly something I told you what's true for groups, and now it also works for this non-commutative principal bundles. Okay, and now I skipped this. This is just to show you how the things look like, but we don't really need this. It's the action, how the multiplication. Here you see a multiplication where you have the twist and then multiplication with the co-cycle. It's a little bit like in group theory, so that we don't have to go through this. And evolution is tricky. Let me just say maybe here, again, the original problem or the original idea for this factor system was to classify these guys. The problem is take your favorite C-star algebra B, your favorite group G, compact group, and ask how many free C-star equivalent systems are there in between. All right. Let me just do this here. You can show that two free C-star equivalent systems with fixed point algebra are equivalent if and only if there's associated factor systems are conjugated. There's this equivalence of saying when two factor systems are conjugated. Well, you know, not so important now. Then you can show that if you have an abstract factor system, so everything from before, you don't necessarily know it comes from a principal bundle. Well, once you have this, you can construct a free C-star system. And this basically means that there's a bijective correspondence between the set of equivalence classes of free C-star systems over B and with structure group G, and this set of whatever this conjugacy means in terms of factor systems. So if you know the factor system, you know how many factor systems there are, you know how many free C-star systems there are. Okay, so now let me come to the last part here. So now I would like to address the problem of extending these principal bundles by group extensions. And here's the classical problem to give you an understanding of what the point is, right? So I have a principal bundle B, principal G bundle over X. Okay, great. And then I have a group extension, possibly non-abelian. Oh. And the natural question is, does there exist a principal G hat bundle, P hat, over X, such that the quotient gives you the original principal bundle back? And then, like, you would like to know if there exists, how many different extensions are there? Maybe now you get a little bit of feeling how this is related already to this spin bundle, spin geometry business. So this is a classical setting. And again, I maybe quickly repeat. So you start with a compact connected oriented Riemann spin manifold, and then you have this twofold covering. You've seen this, and you have seen this definition also. This is what is called a spin structure. So you always have the frame bundle, comes equipped with an SON action, and a spin structure is simply a twofold covering, if you want. So that is commutative. That is this diagram commutes. And if such a thing exists, you call it a spin manifold. All right. The relation, of course, now to the original problem is, I mean, just apply this to the central extension given by the universal cover of SON. So this is an example of this extension problem. And now the existence, as we saw, I mean, this Stiefel-Whitney class has to vanish. So for example, all these spheres are spin for n bigger than 2. Okay. And well, if it vanishes, then the inequivalent structures are parameterized by this H1, as we saw. I mean, this was your question, actually, which you got answered. Okay. Okay, now you can just, put the same text, you just use different letters. You start with a non-commutative principal bundle, and you start with a possibly non-abelian group extension. And then the question is, can I extend this to a bigger free C-dynamical system, which has the bigger structure group, but for which, well, if I look at the fixed points, this should recover my original principal bundle. And if so, can I say something about the amount of possible inequivalent extensions? And why? I mean, one of the specific applications is, okay, when I apply this, let's say you have results about this, I would like to use this extension, right? And then I would say, if I have a principal SON bundle and I can extend it, then I would call it a spin manifold, something like this. And then when I have this, I can do the same yoga as Stefan did. I can just associate the principal bundle with the spin representation. I get a nice vector bundle. I can define a direct operator and so on and so forth. I get a spectral triple. And then I would like to understand what the spectral triple tells me about my original fixed point algebra. So this is the large program, or a large idea. Okay. Here, using this factor system theorem, we were able to provide a full cohomological abstraction to this extension problem. I mean, it's a bit tricky. So basically, I mean, there are a lot of algebraic equations. And if you have a concrete example, what you probably would do is you go to church and then you say, hey, please help me find solutions. Okay, I don't know. I mean, you can write it down. Question is a little bit, can you really solve this? But like example, I mean, for example, for compact abelian groups, this is a little bit easier to grasp. So let me say a little bit about this. And for this, I have to talk about quickly something which I would like to promote, the so-called Picard group of the C-star algebra. So whenever you have a Morita equivalence B bimodule, so Morita self-equivalence, then the set of equivalence classes, this forms a abelian group with respect to the internal tensor product. Oh yeah, if you have two Morita equivalence bimodules, you can tensor them, you get a new one. So this gives you a group, and this group is called the Picard group of the C-star algebra. The Picard group has been computed for some C-star algebras. For finite dimensional C-star algebra, the Picard group is simply the isomorphic group of permutations of the spectrum. All right. For compact space, so now for compact space, I mean, there's this Picard group also in complex analysis. So there, it's line bundles. Here it's a bit more, it's line bundles, the same directed product with the homeomorphisms. So there's also some more non-commutative happening. And then you can also, for the quantum torus, of course, it's computed. So here it's just the automorphism group. If you have a theta which satisfies a quadratic equation, otherwise it's the same direct product. Generally, I would like just to promote or motivate that it would be interesting to learn more about these Picard groups. And then, of course, this will also involve to have to understand bimodule structure over C-star algebras, which is complicated. Okay, so why I'm doing this, let's say I have a compact abelian group and I have a free C-statical system, then I have the following assertions. First of all, each isotypic component is a Morita equivalence B bimodule. It's relatively simple to prove this. So once you're out of this compact abelian, they're only correspondence or Hilbert bimodules, and then they're not so nice anymore. So there's, in a compact abelian case, a lot of nice structure. In particular, if you, taking tensor product, then you know that the tensor isotypic component corresponds to sigma, and pi is isomorphic to the isotypic component of the corresponding sum. All right, and I mean, if you believe this, then the third one is clear. Now we always get a map from the dual group into the Picard group by mapping the representation to the corresponding class of the isotypic component. And this is a group homomorphism which follows by 2. All right, and this is an invariant of a free C-statistical system in terms of the dual group and the fixed point algebra. Okay, and this is called the Picard homomorphism. Okay, another quick intermezzo here is, the question is, if you start with the group homomorphism, does this come from a free C-statistical system? Right, because it's invariant, now you can ask, like, is this realized by something, by a non-commutative principal bundle? And the answer is, yeah, well, if you're lucky. First of all, whenever you start out with such a group homomorphism, I would like to know that you always get a module structure on the unitary elements of the center. This is also because this Morita equivalence bimodules are so nice. In particular, you always get a 3 cohomology class. So each group homomorphism gives you a 3 cohomology class. Great. And so here's the theorem. Compact abelian, you choose a group homomorphism, and then the set of equivalence classes of free C-statistical systems with structure group G and fixed point algebra B, and with a specific homomorphism. Each free C-statistical system has a invariant. Now you ask for all of them which have the same invariant. The following assertions hold. Well, this set could be empty, right? No one says that there exists, but it's not empty if this class vanishes. And this is actually something you can compute here, really, depending on G and so on. But this is classical group cohomology. Okay, and moreover, well, if this is non-empty, then the H2 cohomology classifies or parameterizes all possible extensions. Okay, not too bad. So now you can use this to say something here in this extension problem. So again, everything is compact abelian, and you start out with the Picard homomorphism of this non-commutative principal bundle that you would like to extend. And for this, you need an extension of the group homomorphism where you choose any. All right. And then the only thing you have to check is, it's kind of algorithmic, is, well, first of all, you have to check if this class vanishes, right? If this class vanishes, it tells you there is a principal bundle. And then there's a second condition, because, I mean, just because it vanishes gives you one, it doesn't tell you that it's the right one. And how do you check this? Well, there's always this class here, and this class has to be in the image of the restriction map. This tells you, like, if this is the case, this is the right one, and then you can just do the trick, and then the kernel of the restriction map will give you the equivalent extensions. Okay. I mean, okay, this is something nice you can check. The problem here is a little bit that this result only involves the big groups, the extension groups. They might be too big. You want maybe something that only depends on the small building blocks. You see here you have the dual of the big group. So what I managed to prove recently is this, and this is this basically solves the problem for central extensions. Remember, this is a central extension here. And here, okay, you need to refine the concepts a bit. Here you take the Picard group of equivalence class of Morita's self-equivalence over the C-statistical system. So it simply means that you have Morita self-equivalences which have also some action of the group. And then you choose homomorphism. This has to vanish in the 3 cohomology. And then the inequivalent extensions are classified by this guy here. All right. So at least, and this is something you can compute here, right? I mean, if set is C2, then this is something you can compute pretty easily. And let me just mention how is this related to, I mean, this is, how is this related to a former slide? I mean, here the invariants, they're always contained here in the unitaries of the center of the fixed point algebra. So I mean, here it's a little bit of a refined cohomology. All right. We started a bit later, or maybe I just have 5 more minutes or something, if this is okay. Because something that I would like to tell you about is a concept that I find quite interesting. Maybe you've heard about this, but it's called crossed modules. So what is a crossed module? So it's 2 parts. You have 2 groups, K and L, and you have a group homomorphism from K into L. And then you have an action of L on K, which is the crossed homomorphism. Somehow it goes back. And this is denoted by this eta, such that you have these 2 conditions. But the first one means basically that this map mu is equivariant with respect to this crossed homomorphism and conjugation action on L. And the second one is if you restrict eta to the image of mu, then this is simply conjugation action. Okay. So if you have a crossed module, then you can always show that the image of mu is a normal subgroup, and the kernel must always be central. So what does it mean? In this sense, a crossed module is the same thing as a central extension, for which there exists an action that satisfies these things. Or another point of view is you have a central extension and then obtain the structure of a crossed module. You have to extend the action of n on k, right? If you have a central extension, conjugation action, you always have a conjugation action in a bigger group because theta is central. So it doesn't do anything. And then you have to extend this to an action of L, for which this projection map is equivariant. Okay, why I'm saying this is whenever you have a crossed module, you get a 3 cohomology class. Okay. And here, again, if you've worked with group extensions, each outer action, for each outer action, you get a crossed module, which then has a class here. And if this class vanishes, there exists a non-abelian group extension. So crossed modules naturally appear in the theory of group extensions. And then you have also the concept of crossed modules of Lie algebras. Basically, you just apply the Lie functor everywhere in the definitions. Okay. Why I'm saying this, this original problem, in the context of smooth principal bundles and central extensions, Neb defined a cohomology class, a 3 de Rham cohomology class, which is an abstraction to the classical extension problem. So, moreover, Laurent Genoux and Wagemann, they showed that this actually is a full abstraction, meaning that if this class vanishes, you find this big principal bundle. What is the idea? Basically, you have the global Atiyah sequence. Simply means you have the G invariant diffeomorphisms of B, which project down to the diffeomorphism group, and the gauge, the gauge automorphisms, which are those which are the identity on the base space. And here, here you don't have the whole group, but only those which preserves the bundle class under pullbacks. So this is a little bit subtle here. And now if you have a central extension, you get a new central extension. Well, this is extension of the Gauss group, and here you have this guy. And this actually gives you a crossed module. And the corresponding class, it has a 3 cohomology class, and if you apply the canonical derivation map, this is how you get this 3 de Rham cohomology class. Okay. Now you can do actually the same thing in a non-commutative case. Again, if you start with the free C-state system, you can look at the G-invariant automorphisms. They project down on the fixed point automorphisms of the fixed point algebra, but only those which leave A invariant and which have the kernel, the gauge automorphisms, those which are the identity on the fixed point algebra. Now, I mean, this is a little bit of abstract nonsense because, I mean, you can, for each action, you can write down the sequence. Problem is you cannot do much with it because how do you know what kind of automorphisms on B lift? But for free action, you can actually use vector systems to tell what automorphisms lift and also to describe this automorphism group in terms of the vector systems. And in this context, we were also able to provide a cohomology class that only depends, or that explicitly depends on zeta. So on the smaller building block, not on the bigger. Okay. Basically, again, in a compact abelian case, maybe that's interesting, and the gauge group is isomorphic to the crossed homomorphisms. So this is a nice description here. What is the crossed homomorphism? Well, it's the maps from the dual into the unitaries of the center here, satisfying this crossed homomorphism condition. I mean, it's almost a homomorphism, but here you have some kind of this module structure. And then in a compact abelian case, this is your defining central extension. And then you get this cohomology class. And yeah, you can show if there is an extension, then this vanishes. But so far, I'm absolutely no idea if this is a full obstruction class. So if this vanishes, it's not clear at all if there is an extension. So there's some things are lacking here, like how you can construct free C-state system from this group. Okay. So this is basically what I wanted to say. Thank you.
What's the main motivation for the factor theory you just mentioned?
The main motivation for
the factor theory.
For the factor system theory.
Yeah.
Well, I mean, first of all, my original motivation was I wanted to classify free C-state systems. I mean, I was educated in principal bundle theory, and then I knew there was this nice check cohomology theory. And then I wanted to say, okay, maybe how does it work in the non-commutative world? Because, I mean, even if the Hopf-Galois theory, there's no classification, right? I mean, and then, I mean, I don't know, we came up with this theory to classify them, but then we also figured out it can be used, for example, to do computations. I mean, I mentioned this Atiyah sequence where you use vector systems to characterize the building blocks. And also use vector system theory to, remember I said this here somewhere, if I have a spectral triple here, so I have geometry here, I have geometry here, I can use vector system theory to get a geometry on the total space. So in general, it helps you to do computations, it helps you to prove permanence properties, and helps you to do classification. And also here, like if you want to extend principal bundles, you get equations. Okay, I mean, depending on what you want to do, they're quite hard to solve, but still, I mean, in theory, you can do it. So, I mean, the question, I mean, maybe that answers your question, but I mean, you can ask them the same question, why do you need vector system for group extensions? Well, to get new groups, to study groups, characteristic classes, permanence properties, and so on and so forth. Mm-hmm.
Thank you.
It's more, yeah.
Yeah, so maybe a follow-up question on this vector systems. So I'm a simple mind. I think in terms of algebra, and so there these vector systems look a lot like cross-product algebras, and those are a special type of Hopf-Galois. They are exactly the ones that have a cleaving map. Yeah? And so I guess this is true, right? So this is the algebraic notion corresponding to vector systems would be cross-product algebras or cleft extensions.
So exactly, this is where I'm happy and proud to say no, it's even for everything which is non-cleft. So this cleft C stars algebras, this is the case. Remember one condition was isometry, and the cleft case corresponds to where the isometry is actually a unitary element.
That's very strange. Okay.
So in this isometry, for example, just as an example, I mentioned the SUQ, quantum SU2, and as you know, this is not cleft.
It's not cleft.
It's not cleft.
Yeah.
Still, you have this isometries. So this works for every free system, not only those which are trivial somehow, or like cross products or so on. But again, that what you're saying translates to the case where the isometries are actually isometries, unitaries, which means that the Hilbert. Remember, you could choose this Hilbert. You have to find this Hilbert spaces, and in this cross product setting, these Hilbert spaces are the same as the representation spaces actually. So this works in this thing, but it also extends it for every C-star dynamical system, free C-star dynamical system.
Okay, this sounds very interesting, even though I don't fully understand it. But so this would then probably also answer my second question, because you were saying that you were classifying for a given B all possible C-star dynamical systems such that B will be the invariants.
And exactly, I choose the B and the G, and then I ask which free C-star dynamical systems with fixed point algebra G and B and structure group G exist in between.
And to classify this, you use these vector systems. And okay, my question would have been, okay, this is very strange because this would correspond to cross-product algebras, not general Hopf-Galois. So how can this be true? But you are telling me, okay, it's not only cross-product algebras, it's every Hopf-Galois. Okay.
It's every Hopf-Galois.
Very interesting.
And the thing that which is maybe most instructive to understand here is, where is it? This one here before. Here. So this is basically here. For example, SUQ2. This is an example here of the two sphere, and here you simply have theta, the integers, and then you can use this to this is not empty because SUQ2 is such an example, and then you can actually compute then how the others look like. Would have SUQ2 as it works, but there are not many more because theta. Here this cohomology vanishes, so there's only one.
So can I just ask you what will be the vector system for SUQ2 if I don't have a cleaving map? So how does this look like?
Let me see. So. I have to go back. Here I have my S's, and once I have the S's, I can associate the vector system. Right? If I have my isometries, how I build the vector system out of my isometries. This is my isometry. And here you see actually this is not a unitary. This is a proper isometry.
Okay, I will give this a look in. Thank you.
I'll ask the obvious question then. What about generalizing from groups to actions of groups on C-star algebras to coactions of quantum groups on C-star algebras? That's a fairly easy question, so maybe something more concrete. What about something like Elwood, this freeness?
Yeah, it works. We proved that actually for quantum groups. So the classification is for quantum groups, compact quantum groups.
Okay.
Again, it just makes computations more. But these isometries, all of this works for quantum groups. Then, for example, here, now when I told you about lifting the spectral triples, my biggest problem, or our biggest problem was, okay, I mean, here's no problem. But if I have a quantum group here, how do I define a direct operator? I mean, if you have a compact Lie group, you have the standard constructions. Here, I mean, here are some constructions by Sergey. Yeah, exactly. So, I mean, in theory, because I mean, factor system theory works, right? So if someone has great ideas about spectral triples and quantum groups, you can use the same thing. A G. It could be a C, but yeah, it could be a C. Okay.
So it's no longer a principal bundle, some sort of Q deformation of the final bundle, where it's not a group. It's almost. In fact, what is the geometric product and the geometric C2, on both of those you have basically very, very well motivated, very well made spectral triples. And then in the middle A then becomes the full time. So take what you're doing.
A homogeneous space. Okay, I give a thought about this. Yeah. And in theory, you need to have the. I mean, what you would maybe you start out with the quantum group, and then you have to push down the spectral triple on the G, maybe. We can maybe think a little bit more.
You take the example, SU2, this is like the full flag for SU2, but it goes up to SUN or any OPG where you have torus action, higher rank torus action on the quantum group, and with varying everything should carry.
Yeah, absolutely. I mean, the whole classical theory, it works. I mean, questions like how do you establish these isometries? And this I wanted to show a little bit with this homogeneous space. But you can do it. You just have to find a good symmetry. Yeah, sure. Okay, thank you. Yeah, more examples. More examples. Yeah. My supervisor would be proud. Yeah. Okay.
Okay, then back to that again. The next few talks by Andy Meyer from the University of Aberdeen, and the title is Geometric Methods of Great Vector Spaces.